This is StarTalk. We've got another Cosmic Queries edition for you. An all-purpose general astrophysics Cosmic Queries. And we've got an old friend of StarTalk. He's been on once or twice before. Hakeem Oluseyi. Did I pronounce that right, Hakeem?
Close. Yeah. It's a O and a sh. Oluseyi. Think Oluseyi. Oluseyi. But it's Oluseyi. Yeah.
It's great to have you back on. And I got as my guest co-host, Paul Mecurio. Paul, good to see you, man.
Good to see you again. Hakeem, great to meet you. And
good to meet you.
Great to be back.
Thank you.
Yeah. It's been too long, Paul. And you're a host of the Inside Out podcast.
Yeah.
So, and I was once a guest on that program.
You were, and we got to get you back on. It's been a while. You were great.
Okay. All right. Excellent.
There was a lot of sobbing during the interview, but we cut that out. And
okay. Stop. So Hakeem, you're a fellow astrophysicist,
yes.
Educated at Stanford, and you're right now a professor at George Mason University.
Yeah.
And you've been a busy guy. You've got a memoir, came out a couple of years ago. When did that come out?
This past June.
Oh, that recently?
June. Yeah,
oh,
June 2021. Yeah.
Because your story, you're in the military.
Yeah.
You were, weren't you homeless for a while or something?
Yeah.
Or in the streets?
Yeah. Absolutely. Yeah. I had a couple of bouts with homelessness.
Right.
Not really sleeping on the street homeless, sleeping on somebody's couch, on somebody's floor homeless.
Right. Those are two different levels. Right.
There's different levels.
Okay.
That's right. Yeah.
So, but anyway, glad all that has worked out, and
yeah.
I encourage people to read that memoir. Memoirs, I think, as a genre, are packed with all the lessons anyone ever needs in life.
Absolutely.
And so I'm delighted to have yours as part of that community of storytelling to help people bring shape to their lives. So Paul collected questions from our Patreon supporters, and they're just all-purpose grab bag astrophysics.
It is.
So I know a little bit, you know probably more, so we'll knock this out.
We'll see.
Okay. Wait, just before we begin, what was the title of your thesis, your PhD thesis?
Oh yeah, my PhD thesis was titled Development of a Global Model of the Sun's Atmosphere with an Emphasis on the Solar Transition Region.
That is so weird, because mine was exactly the same thing.
You guys...
Two of us?
It's like we're brothers from another mother. What? Come on.
Okay, so we need sun expertise, right?
Oh,
because
absolutely. Yeah.
The sun seems to always be misbehaving. It burps up gases. It unleashes solar flares. It's got spots. And what have you been doing to the sun?
Yeah, so, I look at how energy and mass are transferred throughout the solar atmosphere. So traditionally, the way we look at it is, by the mid-20th century, we thought we understood stars really well, but it failed at the surface of the star. Because if you look at the surface of a star, you see all these plasma loops and jets and, weird stuff happening, right? That's due to action of magnetic fields. So, I'll tell you what really was cool for me. Now, this, Paul, you're going to probably have thought the same thought. But to me,
because he had the same thesis. He was studying the same subject.
Yeah. But, what we do as astronomers and astrophysicists is that we look at light and we say, oh, here's what the matter millions of miles away are doing and the fields are doing based on our analysis of this light. So I really got into, the interaction of light and matter. So I left graduate school and went into Silicon Valley, and my first patents were on using spectroscopy in semiconductor manufacturing.
So Paul, what were your first patents on?
I invented this thing called sunglasses, Mr. Wise Guy. Okay, so there, which everyone gets to look at the sun. What about solar cycle? I just have a question about solar cycle, right? Was that still a conundrum and not sort of something that we have our head around yet?
Yeah, so we say solar cycle. What we're talking about, for those people who might not know, is, just like planets are like a bar magnet, a planet like the Earth that's spinning fast and have a liquid iron core, so is the sun. But the difference is the sun doesn't have a solid surface. It's plasma. And so, when it gets fully separated, one pole at the top, the opposite pole at the bottom, they then migrate and mix up. And when they're mostly mixed is when we get the biggest flares and coronal mass ejections. And then they pass by and it flips, right? And it just does that over and over.
That's
and each time,
that's an 11-year cycle, right?
Yep, that's an 11-year cycle, or 22 if you go back to the original configuration, right? Yeah, and so the thing is that this so-called source of these magnetic fields we call the solar dynamo. And the people who do helioseismology have somehow, I don't know the details, if you look at the interior structure of the sun, there's the core where the fusion reactions occur. Then there's this region known as the radiative zone where the energy moves out via light. Then there's the outer 30% that's like boiling. We call it the convective zone. So the magnetic fields appear to be generated at the boundary between the convective and the radiative zone. Exactly how? Who knows?
Okay.
I don't know. Maybe someone does.
And if you can answer that, then you can explain the solar cycle and sort of what is behind
yeah.
it. Yeah.
Yeah, exactly.
Interesting.
Well, part of it is that the sun does not rotate as one physical solid object, right? It's that the equator rotates faster than other latitudes, right?
That's right. So, so it's really weird, and it also has, if you look at Jupiter's banded structure, it also has a banded structure in the subsurface that the helioseismologists have figured out. And, and these bands go at different velocities, right? And so, you have this big, difference, like you said, slow at the poles, faster at the equator. But then, there's details within there.
Right. Mm-hmm, and it's the same speed at each pole?
I have no idea if that's the case or not.
Right, can you get back to me on that? Because
I'll go.
No, we have a mission going to the sun, but the sun's very hot, so we're going to go at night. And then we can...
Right. With a glass of water. Pour some...
All right, so Paul, give me some questions.
Yeah, we got a lot of great questions. We have a lot of great questions today. So I'm going to start with Kevin Bond. We know that the Big Bang Theory created the universe, and it's been constantly expanding. Then it begins to shrink and implode on itself. So when the universe reaches that final point of imploding to the smallest point, is that event what recreates a Big Bang Theory and recreates the universe? Now, there's a second part to this, but I think we should do it in two parts, and that's the first part. I got this, guys. Don't worry about it.
I could take this, Hakeem, if you want me to. Okay. I could take this one. There is no observational evidence ever in the history of cosmology to say that we're going to recollapse.
None.
All data has always shown a one-way trip, which has been very unsettling to people who prefer tidy stories where it expands and contracts and expands and contracts, and it's like, no, it's a one-way trip, and it's philosophically unsettling to many.
Yeah.
Do we know why it's only a one-way trip scientifically?
The explosive energy exceeds the gravitational energy that would pull it all back together. That's all it is. It's that simple. So deal with it. And I'll say it. I say it often. I'll say it again. The universe is under no obligation to make sense to us.
I think I've seen that on a T-shirt somewhere.
Exactly.
I don't know. Yeah,
bumper sticker or what?
Marches to its own beat.
That's the interesting thing about this Big Bang thing is because if you hear people talk about it in the public sphere, there's some sort of there's one train of thought that leads me to believe that people think that every 30, 40, 50 years, all the world scientists get together in a room, and the topic is, what's the big lie we're all going to agree on? Right?
That's what they think is happening.
That's what they think is happening, right? Literally, nobody can agree on anything. So, just reading a book written by Albert Einstein or someone else in 1938, right? And so it's called The Evolution of Physics. And one of the things he was talking about is how physical thought what we call the scientific method developed. And so, in the Western world,
I know the other author. It's Leopold Infeld. Right.
That's right. Yep.
Correct. Uh-huh.
And so the thing that he picked up on that I was unaware of. So, one thing I knew that, my fellow Western scientists typically don't know is Ibn al-Haytham, the guy who wrote the Book of Optics and was sort of like,
in the golden age of Islam, very important.
The golden age of Islam, around the year 1021, right? So I was like, why weren't we celebrating 1,000 years of the scientific method in 2021? Because he wrote the Book of Optics in 1021. But he insisted that what we believe to be true about the universe should be consistent with what we observe to be true about the universe. And the thing that Einstein points out is that what we observe can only take us so far because the universe is deceptive and it throws you these clues that can lead you astray.
All the time.
And so like Aristotle et al., they took all the clues in and they came up with a model that was wrong, but was consistent with what they observed. Then Galileo decided to do these mental experiments that you could never actually do in real life. right? He's like, he was noticing that if I roll a ball down one plane, it goes almost to the same height up the next plane. But then if you make the second plane have a shallower angle, it still tries to reach the same height. Now he imagined, what if I got rid of all the friction between the ball and the floor, and I got rid of the friction within the wheels? It would go forever, is what he realized, right? And that's what overturned everything, was him imagining an experiment that we could never do. Now, here's the thing about that. You can take that idea and you can make predictions. And I feel like the Big Bang is the best example of how powerful that technique is. Because unlike other experimental science, where you can control variables, you can't do that.
Dish.
You can't do that with the
universe is not in a petri dish, right?
That's right. So you got to say, if this happened, what must have occurred, and then go look for it. And the fact that we have all these crazy predictions that have all, to high precision, have come to fruition. So I get on that, because the good doctor said observations, right? Everything we observe shows that the universe is not going to collapse. But the Big Bang has gone even further. It's not just what we observed, it's what we could have imagined must have occurred. And then we find that it's there with high precision. So it's not like one idea in competition with others. Like the whole idea of the universe being small and dense and hot and expanding to this point is observed fact.
Yeah, I would add to that in a more simple terrestrial example. If there's a cave and it just snowed and you see bare prints in the snow entering the cave, without ever having seen the bear, you have evidence that there was a bear in the cave.
Absolutely.
Yeah.
There are ways to know without actually seeing.
Right.
But is there some sort of is there some hesitation to sort of theorize on things? I mean, obviously not. I mean, that's what science is about. It's not just observation, but it's about going the next step. I mean, like the fact that the Earth, the Big Bang, it's 13.86 billion, but there's a star out there that's 14, 15, 16
right.
billion.
Yeah.
Right. So
You remember that one?
Yeah.
Oh, you still can't get to sleep on that one. They'll pop up. They'll pop up every now and then. And so, yes, it's a conundrum. And so that's the fun part about being on the frontier. The frontier is full of conundrums. Only some of them get the interest of the press and the public. But what they want to think is that, see, scientists have no clue about anything. And they're all there. No, we keep working on it and we figure it out. That's all.
Yeah, yeah. An example I like to give is, it's not new to me. I mean, I didn't invent it, but it's the damselfly. It lives but a day in a forest, right? Now, imagine you're a damselfly scientist and you're in a forest and you see a tree standing, you see a rotting log, and you see a seed on the ground. You could not think, oh, wow, the seed must grow into the tree, which becomes, right? You got to get lucky.
Which then dies and rots in the thing.
Right. You got to get lucky. You need many generations. You need to make lots of observations. You need people to say, oh, I noticed that when the tree falls, it looks like and I saw the seed fall, right? And you can begin to piece things together, but you still have some gaps, okay? So we just launched the James Webb Space Telescope. One of those gaps is from when the Big Bang radiation was set free, what we call recombination 380 million years ago, all the way up until we have stars and galaxies, right? There's a big gap of no knowledge. The dark ages, reionization, the first stars and galaxies, so even though you know a lot, you don't necessarily know everything, but because you don't know everything, it doesn't mean you don't know a lot.
Right.
Love it.
That's a perfect way of putting it. Exactly.
T-shirt worthy as well.
It sounded dumb to me, but okay.
No, that's brilliant. It's brilliant.
If you want
I didn't say a damn thing while you were talking. It was brilliant.
If you want to rationalize your laziness and lack of knowledge that way, good for you. Go for it. No,
wait a minute. Look, as the one white dude in the conversation, I'm not sure lazy is a word.
Oh, no, I didn't mean it that way.
I know, I'm teasing.
All right, I got another one. We're going to move on. I apologize to the person. This is a tough one to pronounce. Slawik Walzik. Nice Irish boy. Hello, wonderful people. When will we be able to create gravitational waves and use them to send information like we do with electromagnetic waves now?
Woo.
Listen, I don't know, but I'm pretty sure when it's possible, the airlines are going to keep it from happening because
I've been doing that forever, man. I could like flex my pecs and send like gravitational waves out, and
But then you woke up, and then what happened?
then I started flexing my trapezius.
So, Paul, with that question, we're going to take a quick break, and when we come back, more cosmic queries with Hakeem Oluseyi.
Dr. O.
Dr. O, I love it. All right, we'll be right back. Okay. We're back. Cosmic Queries, a grab bag edition on all things astrophysics. So I got one of my colleagues from Professor George Mason University, Hakeem Oluseyi.
Yee! Yeehaw! Yee! That's
Dr. O.
Dr. O.
When I'm up in New York walking through the streets, I hear people yelling, yeehaw, all the time. What?
Oluseyi. That's how
There you
I
go.
finally
There you
did it
go.
right. Oluseyi.
You just need a cowboy hat. When you put that on, you can go yeehaw, and it works. every time.
Yeah. So Paul, just before we begin, you do stand up, right? I mean, not during COVID, but you're a stand up guy.
Yeah, stand up and act. Yeah.
Did we first meet on the Colbert's Late Show?
We first
Was that
met.
when we-
It might have been the Daily Show. I was writing on that show.
Oh yeah. So
performing
you
on
go
that
way
show.
back.
And
That's
then we
right.
connected, and I was a fan.
And now you warm up the crowd there at the Daily Show.
I was a writer on the show, performed on the show to warm up, and then I went to the Colbert Report, and then went to the Late Show with Stephen Colbert, and we've kind of been attached at the hip. And
That's great. It's great to have that tracking. It's great to hear that.
Yeah, we're kind of in the same mindset. Like, there's sort of a core group of us that started at the Daily Show that started that kind of point of view. And Stephen came in a few years after we started the show. And, obviously he was great on the show, and then that led to his own show. So we kind of have a shorthand, know how we like to parse the news and all of that. And when we first started on the Daily Show, we weren't doing just politics and the media's coverage of politics. We were doing everything, music, pop culture. And when John came on board, like 3 years in, Jon Stewart, he focused the show a little, pretty much on,
That's
politics.
right. People forget that the Daily Show long predates Jon Stewart. Right?
Yeah, it was 3 years with Craig Kilborn.
Craig Kilborn, right,
yeah,
right, that's right.
And very lovely locks of golden hair that he had, and he was great because he would read anything. He didn't care about offending anybody or whatever, and he had that very dry. Doug Herzog was the president of Comedy Central, who was involved in creating the show. Really liked Craig from Sports Center. And that's how he got to know. And so it kind of, so anyway, yeah.
Let me run my idea by you, Paul. I call it the monthly show.
Okay.
What we do.
Listen, I think we're going to, it might be a little dated. That's all I'm saying.
It might be.
I have a yearly show I want to do. And
So Paul, what question did you leave off with at the break?
Says, when will we be able to create gravitational waves and use them to send information like we do with electromagnetic waves now?
So let me start that out, and I'll go hand off to Hakeem. Gravitational waves travel the same speed as electromagnetic waves, so you're not gaining anything by this. Plus, they're very hard to make. They take a lot of energy, more so than turning on your laser. So I don't know, Hakeem. Do you think of any advantages to using gravitational waves?
Yeah, encrypted communications in a way, right?
Really?
It's like, I'm going to take my two little pulsars, binary pulsars, and I'm going to move them in this way to create a series of, X's and O's.
Oh, so it's secret messages. Oh.
Yeah.
Oh, all
And the other thing is that.
So I hadn't considered that, of course, gravitational waves pass through everything. If you participate in the space-time continuum, gravity waves will go right on through it. They don't even care. So what you're telling me is you're going to send me some secret message with orbiting pulsars, and then I decode it on the other side, and no one can block it. Right. No one can do anything.
Unless they know, if the Ferengi or the Klingons or, the Borg are trying to intercept, we got them.
We have a geek in the house.
Well, why is this not? Is this being experimented with at all, or is it just too?
Paul, he used to work in the Navy, so he can't divulge any further information.
You'd have to kill me if he tells me. I don't want to die right now.
Well, I could bring you into the lab forever to entertain.
Right. So is it? It's not. Is it either conceivable that this could be developed for that kind of use?
Well, the key thing is what the good doctor said, and then you notice he talked about the amount of energy required, and you notice that I invoked pulsars, neutron stars.
Right.
So
right.
doing it, making them happen is. And so the other question I have is, that's detectable gravitational waves. I don't know it to be the case, but I would imagine that moving any mass will create some sort of, gravitational ripple, just like.
Correct. You just have to accelerate the mass. That's all. So it's not movement so much as accelerating, and that creates the ripple.
Got it. Yeah. Right. So it's a matter of how sensitive can you detect and the signal to noise back, for your system.
Right. So what you're suggesting, implying, is that LIGO, Laser Interferometry Gravitational Wave Observatory, which is our first means of detecting colliding black holes, though that costs $1 zillion and a grant from the National Science Foundation and monies from Congress, that's just our first foray.
Yeah, that's true.
And in 100 years, maybe we get way more sense. That's like Galileo and his first telescope. Yeah. And wait a little while, and we'll be knocking this out. And I can catch you walking down the street, just wiggling your arms in a particular way. So Paul, what's next up?
What do you think is the best?
Wait, who's asking the question, Paul? I want to know who
William
these people
D.A.
are. Gotcha.
What do you think is the best?
I got to step up here. That's 3 questions from dudes. I'm stepping in for the women. I need a question from a woman.
All right. Okay. We'll get you on the next one. Here we go.
Okay.
What do you think is the best strategy to expand broadband internet access to rural areas? I've seen lots of talk about satellite, high altitude tech, but also the concept of using unused TV frequencies between the active ones in the VHF and UHF, which seems far more practical. I think this is important, especially in a pandemic, to achieve anything close to equity in education. And I couldn't agree more. I've said it once, I've said it 1,000 times. Rural Kansas needs Squid Game. And let's get on that, will you? So what is the viability of this?
It's not just rural Kansas. There are a lot of very desolate parts of China, Siberia, and people, live there in Alaska. So you got any ideas, Hakeem? I'm thinking.
I don't.
I mean, isn't that what Elon is trying to do?
He is.
Every time he launches, there's 100 satellites that get deployed.
Yeah, and that's why it's fraught with danger to comment on the topic. But there's the Starlink satellites, right? He's attempted to do that, but I think he's not the only game in town. I cannot say what the best option is, but I think we all agree that there's an injustice in it not being available to everyone. And it's going to further, one thing I think about is how, if you look throughout history, I love to study human history over the universe's history. Dirt poor versus well off. You look at these old movies, right? Today, the average person lives better than a king or a queen in ancient times, just because we have air conditioning,
completely,
and clear water, right? Clean water, but.
And plus, we can all buy and eat a turkey leg.
There is that. We can't.
That's the evidence. Right. We're living like kings.
And there's court jesters. There's court jesters like myself that are everywhere now. So
see, we got Paul Jesus minus the hat. That's what he is.
With the hat, and then I do a little thing, and
healthy and comfy jesters is what we have in the modern world. But the thing is dirt poor is still dirt poor, right? Dirt poor in the Mediterranean. In the medieval times, dirt poor today. They're still pretty darn dirt poor, and the top keeps moving further and further away, right? And so when you move the bulk of humanity, like we are the knowledge animal, right? We're the technology knowledge animal. So what you're doing is you're giving a percentage of humanity access to all of humanity's knowledge, and another group of people are just like, y'all go fetch some water. It's terrible.
But this feels like something sort of going back to what Neil was saying a minute ago, sort of, why doesn't science know everything? But is this sounds conspiratorial, but is it these large carriers have the ability and are sort of holding on to the technology for the later? Like, this seems not that complicated to achieve.
Here's my read on that. Well, no, first of all, one of the problems is it depends on what you needed the communication satellites to do. If it's to actually speak to one another in real time, you can't use geosynchronous satellites for that, because as fast as light moves, the time delay is mostly unacceptable to people if you want witty repartee in a conversation. If it's streaming, then it doesn't matter. You just wait there and it streams and gathers and it buffers and then you play it. The problem is orbiting satellites mostly are equatorial. And so if you are at very high latitudes or very low latitude, high polar latitudes, it doesn't have much satellite coverage. And so, and you always need a satellite over you in order to be sending you the signal. So if you have low-lying satellites, you need more of them for there always to be a satellite above your head. If they're far away, it can be over everybody's head, right? But if they're really low, they can only see a couple hundred miles at a time. So that's what Starlink is putting up. I lost count, Hakeem, how many satellites this boy is putting up into orbit.
Yeah, same here. I just see a new, this number of new satellites went up, right? You see these announcements.
But then isn't there a practical limit to how many can be up there at one time and function and not crash into each other? Isn't there that reality?
There's the Kessler effect. Hakeem, you know about the Kessler effect? You don't know about the Kessler effect?
The Kessel run? The Kessel?
Yes.
And some number of
Star Wars.
Would you get Star Wars out of your head?
What are we? No, I would be a no.
It's called the Wookiee effect, and
so the Kessler effect is there's a guy named Kessler. I think it was when was it in the 70s? He did a calculation. He noted that as our satellite population increases, okay, what would happen if a satellite broke apart and then destroyed other satellites and broke them apart?
Oh,
right. So suppose two satellites collide, then each one, let's say, makes 10 pieces, moving at 18,000 miles an hour. So then each of those 10 pieces hits another satellite, breaking them into 10 pieces, right? So go from 1 to 10 to 100 to 1,000 destroyed satellites. He cited a threshold of satellite density in orbit above which we are at risk of if one satellite gets damaged, they all come out.
Oh, wow.
Because it becomes a catastrophic avalanche of destroyed satellites. So yes, there is a limit. We're not there yet, but and by the way, they showed that in the movie Gravity, and I saw that sucker in an IMAX. That was the Kessler effect.
Oh, you saw it when it breaks, when it hits and breaks up. You mean
everything breaks up, and it kept breaking up, and there's mass of satellite debris. That's why their communication links got taken out.
We already have a solution for this. Because this is how we run our nuclear fission reactors. So all we need is control rods. Just drop some control rods in orbit. Blip, 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 blip. They'll absorb the pieces. Reaction stopped.
Like giant magnetic poles that just anything that's metal, like just that gets stuck to it.
See, that's the problem when you're a scientist and you also have a sense of humor. You might say something wild and crazy and somebody take you seriously.
Well, that's because I'm an idiot and I don't know anything. You could sell me a bridge and I would buy it. So I'm an idiot when it comes to some of this stuff. So,
but we got to take a quick break. When we come back, we'll have the third and final segment of our astrophysics grab bag, Cosmic Queries on StarTalk.
Yeah, Paul.
We're back. StarTalk, Cosmic. Wait. Can I bring the show back in, please? Damn.
I love it.
StarTalk. I'm not talking fast enough. StarTalk, Cosmic Queries. Hakeem Oluseyi. Okay? So now,
you got
as you were, Hakeem.
So, I just made a mistake I made once before, and I just wanted to tell Paul the story. So I used to teach. I was working in Silicon Valley in the daytime, and I was teaching an astronomy course at night at Foothill Community College in the San Francisco Bay Area, which is an international. I know Foothills, yeah. And our guy, Andy Fracknoy, write the textbook. All right.
Well, our guy is there, yeah.
So anyway, I like to make jokes, and so one of my jokes a lot of my jokes are self-deprecating humor, okay? And where I come from in Mississippi, we often turn the TH that occurs at the end of words to an F, okay? So breath is breath, So I would joke in my classes and say Earth. And I'd even write Earth on the board, ERF, right? But I get my first quizzes back and I see that some of the students for whom English is a second language have written Earth on their exam. So
Oh man! Oh, you just messing with them. No, why you gotta do that?
I know. I got to think.
Why you do that?
Hey, Hakeem, they call him into the administration. Listen, you're making our students dumber. We have to fire you. You're the only.
I self-corrected.
And just to get the names out there, the guy we're talking about is Andrew Fracknoy, who's a big astronomy educator. And if you go to the Foothills College website, you'll see that there's a Silicon Valley lecture series, a speaker series there. So this relationship
Hakeem,
goes way back.
So if it's
good to hear that.
T-H-E, where do you put the F on? Is it?
No, it's when it occurs at the ends of words.
Oh, it's got to be the end. Oh,
Yeah.
I see.
Yeah.
So truth would be truth.
Yeah, truth.
Right.
That's right.
Truth would be truth.
Exactly.
Truth. Yeah.
Love it. I do it on purpose.
Yeah. How to promote illiteracy.
No, listen. Oh, it's the exact opposite. It's the exact opposite. Let me tell you my
here we
idea.
go. Yeah,
and,
here we go.
This is from the Cosmic Queries. So
there you go. All right.
I was reading about, linguistics, and I was reading about how the language of intelligentsia went from, Greek to Latin to English. And one of the reasons why this, whatever I was reading, claimed is because the languages are more and more efficient. And one thing about the English language is that it doesn't have as many of the gendered, stuff. But here's the thing. I also looked at what the linguists think about what they call black.
Wait. So the Romance languages, almost all nouns are gendered, right? So you have to then structure the sentence to accommodate the gender of the noun, which has nothing to do with sex. It's just
that's right.
In fact, that was the first usage of the term gendered was in language.
Interesting.
So go on.
It is he that did not answer the door, like that kind of thing.
Yeah.
Okay.
So anyway, if you look at what linguistics think of what they call Black vernacular English or Ebonics, which is, the language of my homeland, then one characteristic it has in comparison to normal English is it's more efficient. So my prediction is that all the highly educated people are going to be saying truth and breath and death because it's so much more efficient.
Oh my God!
It's so much more efficient. What's up?
What's up? Or it could be what up? So you're right.
Yeah.
I just saved the second in my day to focus on something.
No, in fact, but you don't need the what. It's just Paul. It's just what's up.
That's right.
Oh my God! You're right.
What's
up?
All right.
Yeah.
You all right? You all right?
Yeah. Ain't no party like a StarTalk party. The StarTalk party don't stop.
I tried to come up with a slang that had the most number of collapsed syllables in it. Okay, and I worked with this with my son, and this is what we came up with. Right? Ready? Okay. Know what I'm saying? What is that translation of?
Okay. Hey, listen,
Do you know what I am saying?
Do you know what I am saying? Right.
Do you know what I'm saying? Know what I'm saying?
But you know what? You brought up another.
That's efficient, right
another
there.
story.
You can't beat that.
That's impressive. That's impressive.
Know what I'm saying? Know what I mean?
That sounds like a question that would be a final on Hakeem's class that he teaches where he makes people dumber. Like that would be the final question. Is you have to take that sentence that Neil just said and make it into the shortest.
I love what you just said, Paul, because I do make people dumber. Right? I'll tell you why.
You're brilliant.
But that's not the intent of StarTalk.
Listen, hear me out.
Can we get back to the questions, please?
Hear me out.
We got hard-working Patreon members.
Listen,
okay, what?
Did you know? And their Patreon members are going to love this. Did you notice how often I have used the phrase "I don't know"? Right? To me, the key thing is knowing the difference between when you know and when you don't know. And you leave my classes understanding that distinction. Very rarely do people walk in understanding it. I didn't understand it, right? I was in my PhD program, and then Art Walker would say to me, "Do you know that?" And I'd be like, yeah, because he's like,
I guess not.
Do you know that? And I'm like, oh, okay, I'll be back. Yeah, so, that's right. I'm making them dumber. I'm making them know they don't know.
No, you're brilliant. Come on. You want to jump to the next one?
All right. Paul, yeah, go for it.
All right. I'm Leonard Letty. Good morning. Two-part question. Why is the speed of light 186 miles MPS and not 190, 170, or some other speed? And the second part is, if I'm in a spaceship going 0.6 C and have an oncoming spaceship at 0.6 C, isn't the other spaceship traveling faster then that's the speed of light according to my frame of reference. I just want to say, Leonard, I think it's inappropriate for you to ask Hakeem and Neil to help you with an astrophysics exam question. It's clear that you're taking a test right now.
That's what that sounds
exactly.
You are cheating, Leonard.
That's exactly what that sounds like.
I don't know, but I'm going to tune in to StarTalk and get this answer right on this test. So there you go. If you want me to.
All right. So I'll jump in here. So light travels as a wave, and waves. One of the things that surprised me about waves when I was learning about waves as a student is what comes from where. So here's what I mean. Suppose I have a long string and I do my hand like that, right? And I send a wave traveling down, right? And let's say I do it over and over, right? Now that wave that's produced is going to have certain properties. It's going to have an amplitude. It's going to have a wavelength, the distance between the peaks. It's going to have a frequency, how many peaks occur in a certain interval of time. And the wave is going to move at a particular speed. And so it turns out that the frequency of the wave is determined by how, and amplitude is determined by how fast and how much I move my hand, right? But the speed of the wave is determined by the string itself. It's determined by its resistance to its change of state of motion. It's material density, and it's also related to how tight it's strung, right? It's tension, right? So one wants to stop it from moving, and the other wants to move it back to equilibrium. But it's just that. So the question is, if I see a wave moving, like if we talk about the speed of sound, right? What we're talking about is the speed at which waves move through that medium. Okay, so if it's a table, I knock on my table, that sound wave moves through it. It's a different speed than when I speak through the air. It's a different speed than when I clap my hands underwater. And it's because of not what I'm doing, but the nature of the medium itself. So light is an electromagnetic wave. It's moving through the vacuum of space-time. And so the speed of light is a constant, right? So is it set by the medium, which is the vacuum? Woo!
Yeah, so as light goes through a medium, it is stopping and then getting re-emitted in the same direction it came in. And that pause effectively slows down the speed of light in that medium. But between stops, it is going the speed of light. But we don't generally speak of it in that way. We say light slows down in glass, in air, in a diamond, as long as it's a transparent medium for that. But yeah, so that's good. So what you're saying, Hakeem, is the property of the vacuum is such that you get that speed for that wave.
But is there a vacuum? In other words, you mentioned the table and sound going through a table versus in underwater. It is about the environment that you're in as well, right?
But space-time is different, right? So if you look at, so we do these things in these weird diagrams called space-time diagrams, right? And so light happens to be the speed of causality in our universe, right? Nothing can happen faster than that speed. So so it's one of those things where if you look at a space-time diagram, you see, oh yeah, it makes sense where, blah, 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 negative energies backwards in time, you get all this weird stuff happening. So, so I kind of was in a way misleading the audience by saying the vacuum, but it's more like space-time itself.
Got it.
Yeah, but here's the other thing to know about the vacuum and whether or not it's something. So we have the Michelson-Morley experiment, which allegedly showed that there's no ether, because electromagnetic waves, all mechanical waves that we know of, require some medium to travel through, but light was different. So physicists said there must be some medium in space, because how is it this wave we call light propagating without a medium? And so Michelson and Morley did the experiment, and they found that, I don't see any differences. But then in these perpendicular directions along the Earth's orbit and perpendicular to it, if you were measuring a relative speed, they would be different. But then you have this person called, what's his name? Fitzgerald? Not Fitzgerald. What is it?
Lorentz.
Lorentz Fitzgerald. Yeah. So Lorentz comes along and says, well, there's another interpretation of the data. And that is if, one arm got shorter by what we call Lorentz contraction now. So space-time itself. So anyway, now we understand in our highest understanding of knowledge that everything is fields. Space is a field. the reason why every electron is identical is because they're not actual independent entities. It's just like every C note on a piano is identical because it's a vibration on a string of a particular length with a particular, density and such, right? And radius. Yeah. So, these electrons are just evidence of this so-called electron field or lepton field. So, the universe that we live in is not the universe we see, right? And so when you look at these subatomic particles, they get closer and closer to that fundamental nature of the universe, right? So things start to get weird. But I'll stop there because I'm using up so much time.
Okay. All right.
All I know is that
or not.
No, I mean, you just said that you were misleading people like you did in your class using the letter F when it should be TH. I think there's a consistent thing with you with misleading people.
Because that's how he rolls.
No,
he just wants to mislead people, yeah.
Exactly.
Paul, we got time for like one more question, Paul.
Okay, this is Sandra. Okay, we have a woman here. Hi, is it possible that we
But
found
just to be
a
clear,
star
Paul, you only know that it's
16
a woman's name. You don't know that it is a woman.
That's right. I thought that after I said that earlier.
It's got to get accurate, just accuracy in reporting here, okay?
Okay.
That's right.
This is, okay. Sandra, whoever you are, is it possible that we found a star that's 16 billion years old? Methuselah is the star I'm referring to. It's a puzzle to me.
It's a puzzle to us all.
Exactly. Yeah. So when you hear that number, there's a second number or a third that is always cited when scientists talk to each other.
And hardly ever cited when the press reports on it.
Absolutely. Okay. And that is the error bar, right? And there's two types, systematic and statistical errors, depending upon, how you're creating the number. And so my guess is that if you look at the error bars of the star's age, the error bars of the universe's age, that both are consistent. But if you look at the central value, it appears to be an inconsistency. This has happened before, will happen again. All the science is in the error bar.
Or could the star be lying about its age? Just putting it out there.
See, first you said it was a woman. Now you're saying you're lying about the age. Paul, I'm beginning to see a trend with you too, man. So,
God.
Once we make the monthly show, you're going to see.
Yeah, exactly. We're going to make the monthly show.
The monthly show.
But wait, didn't the astronomer Howard Bond with his team come up to bring the number down to like 14.8 using luminosity, oxygen in the star, and rates of nuclear reactions? And
so here's a point. We'll go out with this one. What you want to look at is not the number that's the center of the average that you obtain from the observations. You want to look at the uncertainty in that estimate. And every single measurement ever reported in a scientific journal, when properly reported, comes along with the uncertainty. It's sometimes called the error bars. But error makes you think they made a mistake, but they didn't. Right. It's just an uncertainty. Right. Okay? So I have no doubt that the uncertainties overlap between the age of the universe and the age of this star. There's a deeper problem here. We actually have two independent ways of getting the age of the universe. Forget the star, the universe. And those two numbers are statistically different from each other, where they don't even enter each other's error bars. And it's a cosmic conundrum right now. And the two numbers look like they're close, so what are you worried about? It's because the uncertainties have been beaten down to be so narrow that they don't overlap anymore. And so either we need new physics or something else deeply that we don't understand. So this can and does happen, and it's happening right now with the age of the universe.
And which of those two methodologies do you more subscribe to in terms of measuring the age of the universe?
Well, you're looking at it like Newton versus Maxwell when Einstein was looking at it. But, it could be they're taken at very different times in the age of the universe, right? One is made using the cosmic microwave background radiation, highly precise, very early in the universe. And the other is using different types of standardized candles that are calibrated one off the other. Here's what I mean by that. The way we find out distances astronomically in most cases is by the first method is parallax. So we have a new satellite, Hipparcos, which is doing that with super high accuracy within our galaxy. Then we find stars of known luminosity. They're in various types. The brightest ones pulsate, right? These so-called Cepheid variables. And then we have these exploding stars, type 1a supernovae, which are calibrated off of the Cepheids. So now the question becomes, are Cepheids identical in every galaxy such that we can trust that we know their brightness to within the same percentage within every galaxy? There's some evidence that that may not be the case, right? And so, you know, if there is a variation, I learned the word autochthonous. I used to propose to study this. So, formed where found. Geologists use that word. So, you know, is a Cepheid period luminosity relation universal, or is it formed where found, right? And then it's the same thing with the type 1a supernovae. Do we understand everything about them and their environments and intergalactic medium? So there's so much detail and so much to understand that the cosmic microwave background radiation seems like a much cleaner measurement. But
So if you're a betting man, that's where you're going to put down your money.
that's where I would put down my money. But then there's some things. So here's the other problem, right?
Wait, I have to interject. So
Yeah.
what you just said over the last 4 minutes, there's an entire chapter in the StarTalk book called Cosmic Queries on that subject. And it's called Cosmic Tension, and it tells you how you get the distances and the standard candles and the microwave background and the conflict. It's all in a book, Cosmic Queries, inspired by the fact that we actually have these kinds of conversations. Just letting you know.
Doggone it. Your book is always number one in astrophysics, and I'm getting tired of you.
What?
It's like you, Hidden Figures, the baby book. Look, man.
Hey, can I say something? I have a book. It's How the Cow Mooed. All right. It's a top of the charts of the. I think people should get both books. Between the two books, your book, Hakeem's book, and Neil's book, StarTalk book.
I'm like, wait a minute. Shaq is getting all the commercials. Neil is getting all the book sales. Like, come on.
Come on, give the guy something.
Give me, jeez.
You got to come out with your own cell phone. How about that? Like, forget Google.
Wait, Paul, do you actually have a book out? I didn't know.
No, I don't.
Okay.
I'm actually looking to write a book about my life story because people.
No, I thought because if you can write a book about cows saying moo, you know, the whole story about the cow jumping over the moon, maybe they're actually saying moon instead of moon. See?
Let me write this down and let me steal this idea.
I've already tweeted it, so you
Make sure it's a spherical cow.
spherical cow. Well, you got to up them on that, guys. You got to call it quits there. This has been great. Love this grab bag astrophysics, and by the way, 2 astrophysicists are always better than 1. This is what I think we have concluded here.
Absolutely. It's just a lot of astrophysics love right here. Just
you're feeling it. Totally feeling the love.
Like a big group hug right there.
So, Hakeem, good to have you back. And
thank you, sir.
I trust this won't be the last time.
I sure hope not.
And Paul, it's been too long. Good to see you. Don't be a stranger. All right.
Absolutely. Great to see you.
Neil deGrasse Tyson here, your personal astrophysicist. Keep looking up.